Hello. In this video, we're going to look at triple integrals in cylindrical and spherical coordinates. We're going to start with triple integrals in cylindrical coordinates. Let's go ahead and change from pink to black. So triple integrals in cylindrical coordinates are not going to be very much different than the problems from the previous video where we went over and we did triple integrals and we ended up converting from rectangular XYZ coordinates into polar coordinates for the double integral part of the problem. So I do want to note that this section overlaps significantly with previous sections on triple integrals and then double integrals in polar coordinates. You could say that cylindrical coordinates are really a combination of those two sections. But let's go through them briefly, and then we'll spend most of the video on spherical coordinates. Okay, so what are cylindrical coordinates? Cylindrical coordinates it's a three-dimensional coordinate system, just like rectangular coordinates, which are x, y, z, except you've replaced x and y with r and theta. You've replaced the x and y coordinate with the polar coordinates. So specifically, you have rectangular, which is made up of x, y, z, and cylindrical is r comma theta comma z. So you just replace these two with those two. How do you do the replacement? Exactly the way that you would translate from x and y coordinates into polar coordinates. So you still have all of the translation formulas for polar coordinates. They still apply. Effectively, you're just taking the x, y, and replacing it with polar coordinates. Visually, so we can go through and draw a picture. You can see so with polar coordinates, we treat the x-axis as the polar axis. And so theta is the amount of rotation that is off of the x-axis. And then r is the distance that you move out from the origin, in that theta direction. And then z is the same thing it normally is. It's the distance in the z direction, the distance in the direction of the z axis. So if we were to pick some distance, we'll say that's our distance there. So that distance would be z. And that's what polar coordinates are. Sorry, cylindrical. That's what cylindrical coordinates are. Okay, so in terms of actually doing problems, let's go through and do a couple. What you're going to discover is that doing the problems is exactly the same as doing the problems from the previous section where we had triple integrals and we converted them into polar coordinates by using the information from the double integrals over polar coordinates section. It will be exactly the same. There is no difference. All right, so they give us a triple integral to go through and evaluate, and E is the region enclosed by z equals x squared plus y squared, and z equals 4. Okay. So in terms of triple integrals, the idea behind the triple integral in cylindrical coordinates is the exact same idea as the triple integral in rectangular coordinates. We're adding up. So this is the f of x, y, z from the last section. That's what we're adding up. We're adding up the z coordinate as we go through and go over this three-dimensional object. Okay, so if that's not familiar to you, go back and watch the triple integrals alone section. And I go over in quite a bit of depth, what a triple integral is. You're adding up the value of a function over a three-dimensional object. And so in this case, the function is z. So we're adding up the z value over this three-dimensional object. Okay, so again, the way that I did these in the last section, I go through and I sketch them. I think that's the easiest way. So you've got z equals x squared plus y squared. So that is a paraboloid. Okay, and then we have z equals 4. That is a plane. So let's just pick a spot on our paraboloid. And we're just going to say there's a plane that's cutting through our paraboloid there. And so the way that it would do, it's going to hit there, there. And then if you go in the x direction, there, negative x direction, there. And so we're going to get kind of you could think of it like it's a cap on our paraboloid. And so that's our three-dimensional object. It's the bowl, which has a cap on top. Okay. So to go through and set up the triple integral, the way that I did them in the last section. So we go through and you kind of break it up. You compartmentalize and break it up into two pieces. So we're going to do our first integral. So our first integral, the way that you can figure out what you should integrate with respect to is often to look at what you're given, see how we have z equals and z equals. That's suggesting that we should integrate with respect to z first. Okay, and z first is a top to bottom type integration. So the bottom is the bowl. So that would be z equals x squared plus y squared. And then the top would be z equals 4. Okay, and then we're just going to leave this second part alone. Okay, and then for the second part, what we need to do is we need to identify what the base is going to look like of this object. To figure that out, what you want to do is you want to identify you can think of it as the widest part of the object, or you could think about it if you just looked straight down the z-axis, what you'd see, or you could think about just smashing this object flat, and then what would you have on the xy plane? Those are all the same thing. Okay, and so in this case, what we really care about, the widest point on the object is this. So this is what we'd really like to know the equation for. And to get the equation for that, well, what is it? It's the intercept between the bowl and the plane that's on top. So it's the intercept between these two things. And when you want to find the intercept between two things, you set them equal. So we can go through and do x squared plus y squared equals 4. And there we go. We've got the circle. It's a circle of radius 2. So that tells us that this distance here is 2. Okay. So now Now to go through and set up the second integral, we're now going to translate over into polar coordinates. So when you translate to polar coordinates, so x squared plus y squared, again, we've got the previous page. That's one of our translation formulas for polar coordinates. So we get r squared. The 4 doesn't change. The dz doesn't change. And then we've got the dA. You can put r dr d theta. And then r goes from 0 to 2. I guess I didn't graph the base. You can graph the base. I forgot about that. Right. If you graph the base, and then we've got a radius of 2. And then so with polar coordinates, we want to go from the center of the object all the way out to the outer edge. And so the center is at 0, right, for this circle. It includes everything all the way from the squiggly line here all the way to the center. And so we go 0 to 2. And then we go all the way around. All the way around is 0 to 2 pi. So from there, we can go through and just evaluate. So you get 0 to 2 theta, 0 to 2. The antiderivative of z dz is going to be z squared over 2, r squared to 4, r dr d theta. And so we get 0 to 2 pi, 0 to 2. Plug in 4, you get 16 over 2, that's 8, minus r squared squared is going to be r to the 4th over 2. And then we've got r dr d theta. So from there, we can go through and maybe we can multiply this out. So this, we're going to have 0 to 2, 8r minus r to the 5th over 2, dr d theta. And so we got 0 to 2 pi. And so that's going to be, what's that, 4r squared minus r to the 6th over 16, evaluated from 0 to 2. Oh, and we're running out of space here. Let's see if we can squeeze it in. So 2 times 2, so we're going to get 4 16s. We're going to get 16 minus, and then r to the 6th. I believe that's 64. So we've got 64 over 12. D theta. And I'm just going to pop the answer in here because it's, you can see from what to do from there. You should get 64 pi over 3. All right. Sorry about that. Ran out of space. I don't want to use up the whole next page. So let's so anyway, as you could see, the previous page, we introduced the idea of cylindrical coordinates, and then we went through and we did this problem, and nowhere did we use cylindrical coordinates. Instead, we basically used the triple integral with x, y, and z, and then we used the translation formulas from double integrals over polar coordinates. And that's how you do these problems. Cylindrical coordinates exist. I mean, it makes sense, what they are, but in terms of the context of doing problems, they're not really necessary for doing problems. You can just go through and use the techniques from previous sections. So there's really nothing new in this cylindrical coordinates section. All right, and so because of that, we're just gonna skip ahead to spherical coordinates, because spherical coordinates are absolutely brand new, very foreign, very, dare I say, weird, and frequently a topic that gives students hives. So let's spend most of our time in the video on spherical coordinates. Okay, so first of all, what are spherical coordinates? They're very different. They're very strange. So spherical coordinates, what you do is you start off you start off with theta. So theta, that's familiar. You start off by rotating off of the x-axis a distance theta. So you start off by rotating. And then I'm drawing a line here, but you're not going to go along that line. This is not it's not cylindrical coordinates. It's very different. Instead, this line effectively defines a plane. All right, so what it's going to do is it's going to define a plane. And then what you're going to do, what you do next is you're going to rotate off of the z-axis. You're going to rotate off of the z-axis on that plane a distance phi. All right, so I'm going to go ahead and put a line here for how far we're going to rotate. So let's put a line here. And so we're going to rotate a distance phi. Okay, and those two rotations, so one rotation off of the x-axis to define a plane, and then a second rotation off of the z-axis to define a line. Using two rotations, you can define a line, a direction off of the origin in any possible direction off of the origin, any possible direction. All right, and so two rotations define a direction off of the origin, and then the last piece, because there's three coordinates. The last piece is rho, and that's how far you go out on that line you just created. So let's put a point here at the end, and we're going to say this distance is rho. Okay, and so spherical coordinates are made up of rho, theta, and phi. So again, theta, that's rotation off of the x-axis. Phi is rotation off of the z-axis. And then rho is the distance from the origin. Those three things enable you to define points in space. So we're going to go through and apply some limitations to these. Theta, we're going to say theta is bounded between 0 and 2 pi. We're going to say that phi is bounded between 0 and pi, and that rho has to be positive. Okay, so to look at our picture here, we're saying that theta is between 0, which is the x-axis, all the way around to just up to the x-axis. So essentially, it gives us the full, 360 degrees in direction off of the x-axis. And then the plane that you're going to define, the amount of rotation on that plane, we're going to say it's 0 to pi. The reason is that if you start at 0, you're straight up at the z-axis. And then at pi, you're straight down for the negative z-axis, but you don't go past that. Okay, so you stop when you get to the negative z-axis. These two things combined give us any possible direction without any repetition. Okay, without any repetition. So we're not going through and repeating points. This gives us a unique direction, these two. And then rho being greater than 0, that's how far we go out in that unique direction. Okay, so that's the idea. Let's see if we can go through and, using that idea, try and plot some various points to become familiar with how spherical coordinates work. All right, so we're going to go through and plot 1 comma pi over 2 comma pi over 4. So we go rho, theta, and phi. All right. And so first we start off with theta. Theta is our rotation off of the z-axis, off of the x-axis, and the rotation off of the x-axis, pi over 2, that takes us to the y-axis. All right. And then once we get there, that's going to, so that's defined. So we're going to define the YZ plane. So that effectively defines the YZ plane as that plane that we're then going to rotate phi onto. All right, and then so phi starts off at the z-axis and rotates downward, and it's going to rotate downward pi over 4. So pi over 2 would be all the way to the y-axis, but we're going to go halfway, so halfway to the y-axis. That's 45 degrees. Okay, and then from there we're going to go. So that's going to be our unique direction, and then that unique direction we're then going to go 1 unit. So we go 1 unit. And you get to the point, and that's it. Okay, let's try another. Let's try 1, pi over 4, pi over 2. Again, it goes rho, theta, phi. So we're rotating pi over 4. So starting on the x-axis, pi over 4, that's 45 degrees. That's going to take us halfway to the y-axis, not quite all the way. You can go through and just try and split the angle there. All right, and so that's going to define our plane. All right, and then on that plane, we're going to rotate pi over 2. All right, so starting on the z-axis, we're going to rotate pi over 2. Pi over 2 would be down onto the xy plane. So now we're actually on this, on the line, the initial line that we drew. That's going to be our actual direction for how far we go rho. And then so we're going to go 1 unit along that line. So let's just pick a point here. We'll say this is 1 unit of distance. So that's 1 unit of distance. I don't know why I put the 1 there. There we go. So that's where our point would end up. Okay. So there's a couple examples. I went through and did a couple more that maybe are a little bit more challenging. We try plotting 1 negative pi over 4, 3 pi over 4. Oops, I don't know why I put a negative. I said there's no negatives, no negatives. Let's convert that into, this is what I meant, 7 pi over 4. All right, so 7 pi over 4, since there's no negative thetas, 7 pi over 4, that's going to be all the way around into essentially quadrant 4, the equivalent of quadrant 4. So if we go through here and put the negative y-axis, what we're going to end up with is we're going to end up with this line here. So that's going to be our line that defines our plane. Okay, and in terms of the rotation, so you go all the way around 7 pi over 4. All right, and now onto that, so now we have, here's our z-axis. So off of that, we're then going to rotate 3 pi over 4. All right, so 3 pi over 4, that's gonna go down toward our negative z-axis. So we want to put our negative z-axis on here. And if we start rotating, so we rotate here, this is pi over 2. Okay, so there's pi over 2, and then 3 pi over 4 is another pi over 4 from pi over 2, right? So, you could give it's 1 pi over 4, 2 pi's over 4, 3 pi's over 4. So it's going to be 45 degrees between this line and this line. All right, so 45 degrees, roughly half those two. Okay, and then so off of the z-axis, we rotated down 3 pi over 4 to get that line. All right, so that's our direction, and then we want to go 1 unit along that direction to get to our point. Okay, so we started off here at the x-axis. We rotated 7 pi over 4 into a 45-degree angle in quadrant 4. And then we rotated, and that created a plane, and then we rotated on that plane 3 pi over 4. So this is pointing downward. If you think of this in terms of a room, if we're in this room, it's pointing downward at a 45-degree angle into the room that's directly below the room that's next door to us. That's the idea. Let's try another one. Maybe that one was too hard. So here's 1 comma 3 pi over 4 comma pi. All right, so 3 pi over 4. So again, this is a rho theta phi. So we start off here and we want to rotate 3 pi over 4. So that's going to be 1 pi over 4, 2 pi's over 4, 3 pi's over 4. So it's going to be 45-degree angle in this room that's next door to us. Let's go put a dashed line here. And then here's our, split that as best you can. And so here's our 3 pi over 4 rotation. And then that's going to create a plane. And then off of that, off of the z-axis here that's touching that plane, we then want to rotate pi. All right, so pi. So if you rotated pi, that's going to be 180 degrees. That's 90 and then 90. So that's straight down. So the negative z-axis is going to be our direction. And then in that direction, you want to go 1 unit. We'll go ahead and put a point and say this is 1 unit. All right, so I guess we can kind of try and put the rotation we did. So starting here at z, we rotated all the way down to the negative z. Okay, so that's the idea. Hopefully with those 4 examples, you kind of have some notion of what we're talking about. So you do 2 rotations, and then after you've done your 2 rotations, you then go out a distance, and that is how spherical coordinates are defined. Spherical coordinates have translation formulas, just like polar coordinates do, and cylindrical too, I guess. So the translation formulas are x equals rho sine phi cosine theta, y equals rho sine phi sine theta. That's supposed to be a theta, just to be clear. And then z equals rho cosine phi. There's also x squared plus y squared plus z squared equals rho squared. All right, so those are our translation formulas. Where do they come from? Okay, well, that's kind of interesting. We could spend a minute talking about that. Where do those formulas come from? So if we go ahead and draw ourselves a picture, and we go ahead and superimpose cylindrical coordinates and spherical coordinates on the same axis. what happens? What happens? Let's look. All right, so we're going to get our line. For both of them, this is theta. And then we're going to pick a point on there. And then this is going to be the distance r for our cylindrical coordinates. Okay. And then up from there, we're going to go ahead and put a point. And that is going to be our z distance. And then to get to that point using spherical, we're going to place a line. And we're going to say that this rotation is phi. And we're going to say that this, or sorry, is phi, yeah. And then we're going to say that this distance here is rho. All right, so it's a little busy. You've got theta is rotation off of the x. Then you go out a distance r. Then you go up z. And then if you get that point there, the other way to get to it is going to be by rotating phi and then going out rho. All right. And so what you've got there is you've got a right triangle, right? Okay. So that right triangle tells us that r squared, right, that's a leg, plus z squared equals rho squared. Okay. Well, what do we know about our polar coordinates, our cylindrical coordinates that we have on here? We already know the translation formulas for those. We know that those have x squared plus y squared equals r squared, and tangent of y over x equals theta, and x equals r cosine theta, and y equals r sine theta. So we have these are given as soon as we start using polar coordinates. We already have these inherited from our early discussions of polar coordinate translations. Okay, and so once you've got your triangle there and you've established that r squared plus z squared equals rho squared, we can then use our earlier result from polar coordinates to say that r squared also equals x squared plus y squared. And so you get x squared plus y squared equals z squared equals rho squared. And that's one of our three. Boom. Okay, that one's verified. All right, so that wasn't too bad. All right, how about the others? Okay, to go through and verify the others, we're going to do something tricky. Do you like it when math teachers do stuff that's tricky? So I'm going to take this triangle here. So I really wish I had this angle. Okay, unfortunately I don't. But what I can do is that this distance here, this line here, I could take this line and I could just shift it up and put it here. If I did that, what would happen? I would get that, right? Okay. And then from there, we could go through and say that this is a right angle. Okay. And then now we have, and this is still going to be rho. And then this line is the line that we shifted up. And so that's still going to be r. Okay. And then from there, now we have a triangle where we have phi relative. Oh, and of course, the amount of distance, if you take how far did we move this up? We moved it up z. So this side is z. And so we can go through and get a triangle that has phi in it, relative to rho, r, and z. And then from there, it's really kind of elementary to go through and verify the other three. That's the tricky bit. From there, it's really not too bad. So we could go through and we could say, for example, how about sine of phi equals, sine of phi is going to be opposite over hypotenuse. So that's going to be r over rho. All right. And then, so what does that tell us? That's going to tell us that, oh, wait. Oops. Hold on. And then from there, we can go through and we can multiply the rho over, and we get rho sine phi equals r. And then if you go through and you multiply both sides by cosine theta, you get rho sine phi cosine theta equals r cosine theta. And then what is r cosine theta? That's x. And so we get x equals rho sine phi cosine theta. Okay. And then we can go through and do something similar. So we have cosine of phi. So cosine of phi is going to be adjacent over hypotenuse. So we're going to get z over rho. Okay. And then from there, we're going to get rho cosine phi equals z. All right. And then we've got boom, boom. Those two are verified. Okay. And then it doesn't look like I did the third one. Okay. So, but you could figure out the third one. Let's see if we can figure it out here in real time. This is probably a really bad idea. But what we could go through and we could try tangent. How about tangent of phi? So tangent of phi would equal opposite over adjacent. So that's r over z. And then, so this is sine of phi over cosine of phi. Yeah, this was a bad idea. Equals r over z. And then if we go through and do z sine phi equals r cosine phi. All right, and then what could we do next? We could multiply by rho. If we do that, so we get rho z sine phi. This is what happens when you screw around. Is this going to lead to anything? We'll see. All right, and then we've got rho cosine phi, so that's z as well. So we've got rz equals rho z sine phi. And then the z's cancel. So we get rho sine phi equals r. Am I going to end up just erasing all of this? Hold on here. So we want y. So let's multiply by sine theta on both sides. So we're going to get rho sine phi sine theta equals r sine theta. And then rho sine phi, I'm sure there's an easier way to go through and do this part of the derivation, equals y. We did get there though, victory, right? So, thank God for just screwing around until you get to the result that you wanted. Okay. Yeah, I'm sure there's an easier way to go through and get that third formula. But anyway, we verified all three of them, right? So there's the x squared plus y squared plus z squared equals rho squared. And then there's how to go through and verify the x equals rho sine phi cosine theta. There's y equals rho sine phi sine theta. And there's z equals rho cosine phi. Okay, let's go through and try using the translation formulas. So suppose we wanted to translate from spherical to cylindrical, or sorry, from spherical to rectangular. All right, and let's say that we had a starting point was 3 pi over 2, 3 pi over 4. So again, that's rho, theta, phi. our translation formulas are x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. So it's really simple to go through and use the translation formulas to go from spherical to rectangular. You just take these values and just plug them in into the formula. So we're going to have rho is 3, phi is 3 pi over 4, and then theta is pi over 2. Rho is 3, phi is 3 pi over 4, theta is pi over 2. Rho is 3, phi is 3 pi over 4. All right. So cosine of pi over 2, right, is going to be 0. So we're going to get 3 times, I guess we could do that one. That's root 2 over 2 times 0. So that's going to equal 0. And then here we've got 3. So sine of 3 pi over 4 is root 2 over 2. And then sine of pi over 2 is going to be 1. So we're going to get 3 root 2 over 2. And then we've got 3. Cosine of 3 pi over 4 is negative root 2 over 2. So we get negative 3 root 2 over 2. And so our rectangular coordinate point is going to be 0, 3 root 2 over 2, negative 3 root 2 over 2. Okay, and real quick, in case you're wondering, how did he go from here to here? Or from here to here. If you don't remember how to do that, what I did there is I went through and I used the reference angle and then our handy little formula for figuring out the sign of sines. All right, so we have, A, S, T, C. So all three are positive in all of the trig functions are positive in the first quadrant. Sine is positive in the second, tangent in the third, cosine in the fourth. Okay, so 3 pi over 4 is going to be over here in quadrant 2. The reference angle for 3 pi over 4 is pi over 4. Sine of pi over 4 is something that you should have memorized. That's root 2 over 2. And then sine is positive in quadrant 2, which is where 3 pi over 4 is. And so you get positive root 2 over 2. Cosine of 3 pi over 4, the reference angle for cosine of 3 pi over 4 is pi over 4. And then cosine of pi over 4 is one of those you should have memorized. That's root 2 over 2. And then 3 pi over 4 is in quadrant 2. Sine is positive in quadrant 2. That means the other two are negative. So cosine is negative. So you get negative root 2 over 2. So that's just a quick little handy refresher on how to go through and do trig functions for, with reference angles. All right. So moving on, we want to go through and what about translating from rectangular to spherical? All right. So again, this time we have negative 1, 1 root, negative root 2. So this is x, y, z. So how do we go through and translate this into spherical coordinates? So we want to use the translation formulas, but the one we want to use first is we want to go through and use x squared plus y squared plus z squared equals rho squared. So you want to use that one first. Take these and just pop them in. So we're going to have negative 1 squared plus 1 squared plus negative root 2 squared equals rho squared. And then you get 1 plus 2 equals rho squared, 4 equals rho squared, and then rho equals 2. Okay, so that's one. That's one of our three spherical coordinates. And then to go through and find phi and theta, so there's an order. I should explain this. There's an order to translating from rectangular to spherical. You always want to do this one first. Once you've done that one, the next one you want to do, right? Let's just take a look at them, right? So if you look at the 3, you want to do the next one you want to use the one that only has one of the two variables that's left, right? You don't want to use both, because if you go through and you plug in the y coordinate and rho, you're going to have 2 unknowns. So you want to use the z coordinate next, and then go through and find, to find phi, and then go through and find theta last. All right, so next we're going to go through and use z equals rho cosine phi. So we know that z is negative root 2, and we know that rho is 2, and then we have cosine of phi, and so we can get negative root 2 over 2 equals cosine phi, and then that tells us that phi equals 3 pi over 4. Okay, and that's very similar to what we did on the previous page in terms of figuring this out. So if you've got cosine equals some multiple of root 2 over 2, then the reference angle is going to be pi over 4. And then whereas cosine negative, it's negative in quadrant 2. So you just want pi over 4 in quadrant 2, which is 3 pi over 4. All right, and then once you've got 2 of them, you can go through and use either formula to find the last one. So we can do x equals rho sine phi cosine theta. So we've got x is -1, and then rho is 2, and then phi is 3 pi over 4. So we're going to get sine of 3 pi over 4, and then cosine theta. All right, so we get -1 half, and then just move the 2 over, and then 3 pi over 4, we're going to get, so sine of 3 pi over 4, that sine is positive in quadrant 2, so we're just going to get positive root 2 over 2, and then times cosine theta. All right, and then if you move this root 2 over 2 over, you're going to get the 2's in the denominator are going to cancel. You're going to get -1 over root 2, which is the same thing as root 2 over 2. So root 2 over 2 equals cosine theta, and then theta also equals 3 pi over 4. Okay, wait, is it 3 pi over 4? Wait, hold on. Let me, I'm going a little bit too fast. All right, the way to tell here, let's just take a look at this. Nope, almost went by that too quickly. When you find theta, the issue with theta is that you're going to have 2 possibilities for the angles. So yeah, let's just slow that down a little bit. I went through that too fast. Maybe that's not right. You're going to have 2 possibilities because there's 2 places where cosine theta can be negative. Now, in the earlier example, this one, there's only 1 place where cosine could be negative, and that's because phi is between 0 and pi. Remember, phi is between 0 and pi, so there's only 1 possible place where cosine could be negative, and that's in quadrant 2, right? Again, if you only have 2 quadrants, cosine's positive in quadrant 2, or negative in quadrant 2. All right, now cosine, if you got 4 quadrants, then cosine is negative in 2 of them. It could be negative in quadrant 2, or it could be negative in quadrant 3. To figure out which one of those you have, whether you have quadrant 2 or quadrant 3, you've got to look to your x and your y. They'll tell you. All right, so if x is negative and y is positive, where is that? That is quadrant 2. All right, well, so we were right. I was right the first time. It was 3 pi over 4, but that was luck, essentially. If x had been positive and y had been negative, then it would have been over here in negative. It would have been over here in quadrant 4. Okay, because if x is positive, then this would have been positive, and then we would have had a positive angle with a negative y. That would have been over here in quadrant 4. But that's not what we had. We had -1 for x and +1 for y. So that's in quadrant 2. Okay. Next. There are some spherical objects that you really do need to know about, have a little bit of experience with. You may or you may not encounter them when you're doing the homework, but these are just common objects that you can have with spherical coordinates. So they're a little bit like, in terms of rectangular coordinates, it's a little bit like having, a cylinder where x squared plus y squared equals r squared. As soon as you see it, it's a cylinder. So there are some objects like that. All right, so the most common and the most important are spheres. Okay, so I'll put an example. Rho equals 3. If you see rho equals 3, this is a sphere of radius 3. Why? Why is that? Well, the reason is that just like in our other coordinate systems, if a variable is missing, then that variable could be anything. If there's no mention of rho and there's no mention of phi, I'm sorry, if there's no mention of theta and there's no mention of phi, then that means that both of those two things could be anything. And so you could have any direction and then a distance 3. Well, what is the set of points that's any direction from the origin, and 3 distance away? That's a sphere of radius 3. Okay, and so that's the idea, is that if you have rho equals, then theta and phi could be anything, which means that you could have all of the points that are at that distance from the origin as possibilities. The second one that's really easy are cones. And this is the main objects you're going to see in spherical problems are going to be spheres and cones. And it's just because it's really easy to represent those things. All right, so think the same thing as the previous example with spheres. We don't have a rho, which means that we could go any distance away from the origin, and we don't have a theta, which means that we don't have a rotation off of. We could rotate any distance off of the x-axis. The only thing we have is an angle phi off of the z-axis. Actually, what I should do here, I should draw pictures. All right, let's just go back briefly to the previous one. I should have drawn you a picture. Right. If you go through and you've got all the points that are 3 units away from the origin, and you go through and you just plot them all, you're going to end up getting a sphere. Okay, if you've got if you rotate pi over 4 in every direction off of the z-axis, you've got pi over 4 here and pi over 4 here and pi over 4 here and pi over 4 here, you're going to end up with a cone. Try that again. All right, so the bottom part is the cone. So these lines are the bottom of the cone. Oh, it's ugly. That's ugly. That's an ugly picture. All right, so the idea is you've got this. That's not much better. It's hard to draw cones on the writing tablet. Oh, geez. Man, I cannot get that one line right. Actually, let's just go back to the original picture. I only just clean up the original picture. That's easier because I'm actually using the line tool. All right, so this is the 45-degree angle in the, between the x-axis and the z-axis. Here is the 45 in the negative, between the z-axis and the negative x-axis. And then we've got the 45 between the z-axis and the y-axis and the negative y-axis. And then there's the 45 between the y-axis and the z-axis. That's as good as it's going to get. That's a cone, right? You agreed. Nod your head. All right, cylinders. So you can represent cylinders in spherical coordinates. It's just more difficult. Oh, by the way, I'll label this. This is pi over 4. It's a pi over 4 cone. So what you can do is if you go through and you start off with x squared plus y squared equals, oops, this is turning into a mess. You start off with x squared plus y squared equals 4. So that's an example. We know that's a cylinder. What you can do with this is you can go through and you can plug into this. So we know that x equals rho sine phi cosine theta. And since we're squaring, we just square all those. And then we have y squared, so that's going to be rho squared sine squared sine squared. Right, and notice how these two are exactly the same, except you've got sine squared for one and cosine squared for the other. That means we could factor out a rho squared sine squared and end up with 1 for the rest. So this is going to be rho squared sine squared phi equals 4. And then from there, you could square root both sides and you get rho sine phi equals 2. And then if you divide the sine over, you're going to get rho equals 2 over sine phi. This format here, that is what cylinders look like. All right, so if you want to go through and create a cylinder, you can go through and create a cylinder using this little formula. So if you have x squared plus y squared equals 9, then that would be rho equals 3 over sine phi. So this is the radius of the cylinder. All right, so the radius of the cylinder goes here, and sine phi goes in the denominator, and that gets you a cylinder. Okay, so that's something that you could potentially encounter. All right, and I'm not going to draw you a picture of a cylinder. People know what cylinders look like. All right, what else? You could also encounter planes. Lots of different types of planes. Okay, so let's look at example planes. Let's suppose you had the example plane x equals 2. So what is x equals 2? What would that translate into in spherical coordinates? Well, if you go through and replace x with rho sine phi cosine theta equals 2, then you're going to get rho equals 2 over sine phi cosine theta. So this is the formula for a plane that's parallel to the YZ plane at x equals 2. This is the location of the plane. And this is a plane that's parallel to the YZ plane. And then you could go through and do the same thing for the others too. So if we do y equals 2, then you get rho sine phi sine theta. And then you get rho equals 2 over sine phi sine theta. So that is what a plane in spherical coordinates looks like. This one is a plane that's parallel to the XZ plane. So 2 again is the location. And then our last one, z equals 2. You get rho cosine phi equals 2. And then rho equals 2 over cosine phi. And that gives you your equation for what planes that are parallel to the XY plane look like. Right, again, and 2 here is the location. So it was started with z equals 2. If this was z equals 5, then we'd have 5 over cosine phi. Okay, and so that's what planes look like in spherical coordinates. You may or you may not encounter those in homework. All right, so that is spherical coordinates. Next, now that we've introduced them and we know what they are, we can finally look at triple integrals in spherical coordinates. All right. So the idea is very similar to the idea. So the idea of triple integrals is the same as the idea from just plain triple integrals. The idea for triple integrals in spherical coordinates is the same as the base triple integral idea. You're adding up a function over an object. The difference is that the object in spherical coordinates is a spherical shaped object. I will try to draw you what that looks like. It is not easy. So I'm intentionally going to go through and draw it over here. Make it kind of thin. Makes it a little easier to. All right. So the idea is that we're going to have the first one side of our object is defined by theta equals alpha, and the other side of our object is defined by theta equals beta. They're both rotations off of the x-axis. So you rotate alpha to get to the front, you rotate beta to get to the back. Okay. And now off of the z-axis, we're going to have we're going to have rotations. We're going to have two rotations. So we're going to have gamma, and then see if I can do this, delta. Those two are directly, they're on the plane that's defined by theta equals alpha, like we talked about earlier, how the rotation defines a plane. Those two are on the plane for alpha. And now we're going to try and draw two more that are on the plane for beta. Let's see if we can do this. So that one's up on the plane for beta. Let's see, where should this one be? It feels like it should be right on top of the other. Let's do this. It feels like it should be right on top of that one. Let's put it there. Maybe that gives you the best. All right. And then, so the object itself here is that, and then the next thing we're going to do is we're going to go through and we're going to define distances that are going to be functions for rho. So we're going to pick a spot here and a spot here. All right. And those are going to correspond to, and then we're going to have a corresponding, oh, hold on, sorry. We need two more spots yet. So we're going to have 4 spots. These are going to form the bottom surface. Like you can think of it like a sheet, the bottom sheet. All right. And that sheet is not necessarily smooth. So we can go through and have, something like this, something like this. Now this side is smooth like that and like that. So that is defined by, that is rho 1 of theta comma phi. And now we're going to have further out on our object, we're going to have another sheet, and that doesn't have to be smooth. This is, so we have sharp edges here and here though. And then that is defined by rho 2 of theta comma phi. All right, and so you can kind of see a 3-dimensional shape there. So that 3-dimensional shape has, this side, let's see if I can use some colors here. This side and this side, it's kind of hard to see it. Those sides come from differences between 2 angles, right? So they're not parallel. So they're not parallel like with straight triple integrals, right? They're at an angle to each other, all right? And that angle is going to come from our rotations, which I forgot to label, off of the z-axis, right? So they come from this side is defined by phi equals, I guess gamma, and then this side is defined by phi equals delta. All right, and so they're come from 2 angles. And now it's a little hard to see here, okay, but they're also, so they're smooth, they're flat, they're like a flat object, but they're not parallel though. And then on this side, right there, and then on this side, the back, I'm gonna erase this blue stuff in a second, but I just want to illustrate this. The sides, those are also smooth. Those are also flat, and they are directly above these two angles. And so they are also at an angle to each other. They are also not parallel. They're at an angle. Okay. And so you've got a bunch of different things that are at these angles to each other that are all going down into the origin. And so that forms this strange looking shape. Let's get the blue off there so you can kind of see it more. Oh, geez, we're erasing the whole thing, I guess. That was a bad idea. Okay, there it is again. And so this object is what we're going to end up adding up our function over, right? So let me just go over some of the basics for triple integrals again. So what you're doing with the triple integral is you've got f of, we're going to use spherical coordinates here. We've got f of rho, theta, and phi. Those define a value at every point. And then we also have a three-dimensional, we also have a three-dimensional object B, all right, and that's what's pictured here. That's this three-dimensional object that I've drawn here. It has this strange shape. And the idea behind a triple integral is that we are adding up the value of f over b. So we're going to every single point inside of b, we're figuring out what the value of f is there, and then we're adding all those up. So that's the idea of a triple integral. If that's brief explanation doesn't make any sense, go back and watch the beginning of the triple integral video again, because the concept is the same here. It's just we're using spherical coordinates instead of rectangular coordinates. Okay. So in that video, one of the things that we ended up doing is we ended up figuring out how do we add up f? How do we go through and add up f? And the answer in that triple integral video was to go through and take f and multiply it by change in x, change in y, and change in z. All right, so that's the way that we added that up. We created a cube whose volume was change in x, change in y, and change in z, and then we multiplied volume by f. All right, so this is kind of just a recall from the triple integral video. To add up f, we used f times change in x times change in y times change in z. Right, this came from the volume of a cube. And if none of this makes any sense, go back and watch that triple integral video again, the beginning. This whole part, this whole part will be explained adequately there. I'm just recalling it. All right, so the question is, how do we go through and add up f inside of this? We can't use cubes. All right. The issue with cubes, if you try to fit them in here, the cubes don't fit smoothly against the sides. They're not going to fit smoothly against the sides that are above our angles alpha and beta. They're not going to fit smoothly against the sides for gamma and delta. They don't fit. They don't have the right shape. All right, so what you need is you need a shape that's going to fit against these angled sides. All right, and so that's the next thing that we need to do is we need to go through and figure out what that shape looks like. All right, so I will try to draw that shape for you. It is not easy to do though. All right, so you start off, got a point, and then everything comes off of the point. So we're going to go out a distance here. And then next to that, we're going to go out a distance next to that. and then we're going to go out a distance below it. And then one more like that. And then the idea is we have like that on the back. And we're going to pick some points over here. And we're going to have that again on the front. So we get this shape, right? So it looks a little bit cubish, but this is curved. This is curved. And these sides, the sides are not parallel, right? They trace back to a single point. If they were parallel, they would stay parallel forever. They would never meet at a point. So this shape is the equivalent of the cube from the previous video. So what we want to do is we want to find the volume of that, and we want to take F times the volume of that, and that is going to be the object that we move around inside of this shape to add up all of the F, all of the function value. All right. So I'm not going to go through a derivation of this. The derivation is quite difficult. I'm going to label some stuff on it. So what we're going to do is we're going to say that the vertical angle here, the vertical angle this way, we're going to say that's change in phi. And we're going to say the angle this way, we're going to say that's change in theta. Okay. And then we're going to say this distance here from the front to the back, we're going to say that's change in rho. Okay. And then we're going to pick a coordinate on here, and we're going to say that's rho sub I. Now you could pick here, or you could pick here, or anywhere. You could pick any spot inside here where rho sub I is. It doesn't matter where that, the specific spot. It just needs to be somewhere inside of here. And then similarly, we're going to pick a spot. We're going to say the same. We use the same spot, but we're going to say we have phi sub j. We're going to say this spot here corresponds to rho sub I and phi sub j. Now, it doesn't matter specifically where that is. This could be rho sub I, phi sub j. This could be. All you need is a spot somewhere inside of here, right? Because what we're going to do is we're going to end up taking the limit as the number of these shapes goes to infinity. And as they go to infinity, they're going to shrink down really small, and the rho sub I, phi sub j, whatever the spot is, they're going to end up being infinitesimally apart. They're going to end up basically being on top of each other. So we're going to say this spot is where rho sub I, phi sub j is. All right, with all that labeled, you can go through and you could do it. There is a derivation for this, but the volume of that shape is going to end up being rho sub I squared sine of phi sub j times change in rho, change in theta, change in phi. All right, and that means the amount of F, amount of function, the amount of F value is going to be F of rho sub I, theta, I guess we'll do K for that since we were used J for phi, and sub J times that. Okay. And then next thing what I'm going to do is once we've found the amount of F, it's just a matter of going through and doing summation of that F of rho I, theta K. We're just going to vary I, J, and K across the object until we go through and end up getting the entire object. And we end up getting all the F values. So we're going to go through and we'll vary I equals 1 to, I don't know, N, J equals 1 to M, k equals 1 to O, and take the limit as mn and n go to infinity, mn and O go to infinity. And then I'm going to skip over the kind of part where we fool around and turn these into integrals one at a time. We're just going to jump right to our integral f of rho theta phi rho squared sine phi d rho d theta d phi, and where these integrals are over our object, which did we label it B? Yeah, three-dimensional object B. And so that's the somewhat brief derivation for what a triple integral over spherical coordinates looks like. And the main difference, of course, is that we've got these different letters instead of X and Y's and Z's. The main difference are those, plus you've got this piece here. So don't forget this piece. When you're doing triple integrals, you need this rho squared sine phi. That comes from the volume of the little object here that we're going to move around inside here. We're going to draw a bunch of those inside here to end up adding up all of the function inside. Just like we drew cubes inside for the triple integrals, we're going to draw these shapes inside of this object to add up all of the function value inside there. Okay, so that's what the triple integral over spherical coordinates looks like. Now let's go through and do some examples. So evaluate. We've got our object. They're using E instead of B. I don't know why, but that's what they're using. X squared plus Y squared dV, and they say E lies between the spheres X squared plus Y squared plus Z squared equals 4, and X squared plus Y squared plus Z squared equals 9. All right, and so you can go through and sketch the object. That's often helpful. So what do we got? We've got radius 2, radius 3, 2 and 3, 2 and 3. We've got an inner circle, sphere, and then we've got an outer. For the writing tablet, that's actually not terrible. So what we want is we want to go through, and E is between the two spheres. E is this stuff inside here. Okay. All right, so to go through and evaluate this using spherical coordinates, we first need to translate it over into spherical. So what does that translation look like? Well, first of all, spherical coordinates do not have X's and Y's in them. They have rhos, phi's, and thetas. So you need to change from X squared and Y squared. You need to change these over. And so the way that we can do that is we can use our translation formulas. We know that X equals rho sine phi cosine theta. So we're going to get rho squared sine squared phi cosine squared theta. And then Y, we get rho squared sine squared phi sine squared theta. That's changing those two over. And then dV, that's going to be rho squared sine phi d rho d theta d phi. And then what are our bounds going to be? So our bounds are going to be in terms of spherical coordinates. So we can look at our picture to try and figure them out. All right, so what would the rho bounds be? Well, we've got two spheres The great thing about spheres is that spheres are really easy to describe with polar coordinates. So the sphere in, or sorry, spherical coordinates. A sphere in spherical coordinates is defined by rho equals the radius of the sphere. So what's the radius of this inner sphere? The inner sphere comes from this, r squared. So it's going to be 2, right? 4 is 2 squared. And then the outer sphere is from rho equals 3 squared would give us 9, so 3. And so we're going to get from 2 to 3. And then theta, so theta is, if you think about rotating off of the x-axis, what part of the object is, how far do we have to rotate to get the object? Well, you rotate, the object is at the x-axis, so you start off at 0 and you rotate, and it goes all the way around. It goes all the way around the circle. So you'd get from 0 to 2 pi. And then what about phi? So is the object where the z-axis is straight up? Yes, it is. And then does it go all the way down to the negative z-axis? Yes, it does. So you want to go 0 to pi. All right, and that's all there is to it. And then from there, it's just a matter of going through and simplifying. So we've got 0 to pi, 0 to 2 pi, 2 to 3. This, we simplified this earlier. This simplifies into rho squared sine squared phi times rho squared sine phi d rho d theta d phi, 0 to pi, 0 to 2 pi. Well, this is rho to the 4th, so we're going to have rho to the 5th over 5. 2 to 3 sine cubed phi d theta d phi. Plug in 3, that's 243 fifths minus 32 fifths. 243 minus 32, according to my notes, that's 211 fifths. Let's just use that to speed this up. Then we're going to get sine cubed phi d theta d phi. So when we're integrating with respect to theta, we would treat phi as a constant. So we're just going to get theta. So it's 211 fifths, 0 to pi, theta, 0 to 2 pi, sine cubed phi d phi. And so plugging in 2 pi, that's going to give us 422 pi over 5, 0 to pi, sine cubed phi d phi. And so we want to go through and to evaluate that integral, you want to split this up into sine squared phi times sine phi d phi, not theta, d phi. And then sine squared can be turned into cosines. And so we're going to get 1 minus cosine squared phi sine phi d phi. And then we want to go through and do u equals cosine phi. du is negative sine phi. So we need a negative there and a negative there. And I think we got enough room to, we could do this on this page. So we're going to have negative 422 pi over 5 integral. Change the bounds, so take 0, plug it in, cosine of 0 is 1, takes pi, plug it in, cosine of pi is -1, and then we're going to have 1 minus u squared du. And that's going to be negative 422 pi over 5. The antiderivative of this is going to be u minus u to the 3rd over 3, 1 to -1. Yeah, maybe we're not going to have quite enough space here. Let me just try and squeeze it in. This is going to be negative 422 pi over 5. And then here, if you plug in -1, you're going to get -1. Plug in negative 1 to the third is going to give us -1/3, but times a negative. So we're going to have plus 1/3. And then minus, plug in +1, you get 1. Minus, plug in 1, you get 1/3. Distribute this negative. So we're going to have minus, plus. So this is going to be -2 plus 2/3. Times negative 422 pi over 5. Right. And so what is that? That's -6/3. -6/3 plus 2/3. It's going to be -4/3. We're going to have -4/3 times negative 422 pi over 5. And that's going to be something, right? So what is that? That's going to be, we got 1688 pi over 15. Something like that. Anyway, that's a long example, but there's an example. And if there's some mistakes in here, you can point them out in the comments. All right, let's do another one. We have square root x squared plus y squared plus z squared dv, where E lies above the cone z equals square root of x squared plus y squared, and between the spheres x squared plus y squared plus z squared equals 1, and x squared plus y squared plus z squared equals 4. All right, so first of all, we've got to figure out, what does this object look like? All right, and so it lies above the cone. All right, so what is this cone? So don't forget, if you have trouble graphing something, you can always use the cross sections, from the earlier contents. You go back and watch the quadric surfaces video. I explain how to go through and graph these. But the way that you could think about it is, if you plug in y equals 0, then you're just going to get z equals the square root of x squared, which is z equals plus or minus x. Z equals plus or minus x looks like this. All right, so there's z equals positive x. There's z equals negative x, right? Where here's the negative x-axis. So it's the line that has a slope of 1, right? A line with slope of 1 on the xz plane, the positive xz plane, and a slope with a line with a slope of -1, on the negative side of that of the xz plane. All right, and so that's our sides of our cone, 2 parts of our cone. And then if you go through and you set x equal to 0, you get z equals y squared, which is the same thing as z equals plus or minus y. Z equals plus or minus y is going to be the cone that goes this way. All right, and that's the line that has a slope of 1, between the y-axis and the z-axis on the yz plane, and then a slope of -1. And so from that, you get a cone. All right, And then, so it lies above that cone. So we want to be above that cone. Anything below that cone, we don't care about. And then it needs to be between two spheres. So now if you imagine drawing spheres, so there's a sphere, just pick a spot here. We'll say there's a sphere that's down there. So that sphere, the part of that sphere is going to be like that and like that. And then there's a sphere, we'll put it up here. And the part of that sphere is going to be like that and like that. Okay, and so what you've got is you've got this the cone, and then there's like a rounded top and a rounded bottom. So it's a bit like the difference between two ice cream cones. So they'll give you a top ice cream cone and a bottom ice cream cone, and you somehow subtract the two. That's this region. It's between them. All right. So once we know what the object looks like, we can go through and set up our problem. So first, if we're changing over to spherical coordinates, we need to get rid of these x's and y's and z's. And the easiest way to do that with this problem would be that one of the translation formulas is x squared plus y squared plus z squared equals rho squared. So we could just pop in a rho squared. And then for dv, we've got rho squared sine phi, don't forget it, d rho, d theta, d phi. And then the bounds here, let's take a look. The bounds, all right, well, if we look at our object in terms of rho, right? So in terms of rho is going to be between the spheres. So between the spheres. So we've got a sphere of radius 1 and a sphere of radius 2. So we're going to go from 1 to 2. And then next we have theta. So theta in terms of our object is going to be the amount of, think of it in terms of the object, the amount of rotation off of the x-axis. So is there any part of the object that's above the x-axis? Yes, if you go from the x-axis, you just go straight up, you're going to hit the object all along this line here. So part of the object is above the x-axis. And if you went through and rotated, the object is above, if you took this arrow here and you rotate it around, the object is above that arrow the entire time, all the way until you get back to 0 again at 2 pi. So we want to go from 0 all the way around to 2 pi. Okay, if the object had stopped at some point, then you want to stop the amount of rotation. Like, so for example, maybe potentially this object, we would have not had they could have said, we don't want any part of the object that is on the negative side of the xz plane. Then you would have gone from 0 to pi and you would have stopped there. All right, and now in terms of phi, so phi is our rotation off of the z-axis. So first of all, is the object straight on the z-axis, straight up? Yes, and so you want to start at phi equals 0, and then you want to rotate down until the object stops. So the object stops. So where does the object stop? What's this distance in terms of phi? Well, this is the line that has a slope of 1. That's also a 45-degree angle. So we want to stop at pi over 4. Okay. And then from there, it's just, evaluating, simplifying. The pain in the butt part. Rho squared is rho times rho squared is rho cubed. D rho, d theta, d phi. So we get 0 to pi over 4. These problems take a lot of space. So you got to be careful that rho to the 4th over 4, 1 to 2, sine phi, d theta, d phi. Oops, that's supposed to be a 4. Zero to 2 pi. 16 over 4, that's 4 minus 1/4 sine phi d theta d phi. That's going to be 0 to pi over 4. What do we got? 16/4 minus 1/4. That's going to be 15/4. I guess we can just leave that in here. 0 to 2 pi. Wait, hold on. Let's just do this all at once. So the antiderivative of d theta is just going to be theta. So we're going to have theta 0 to 2 pi. And then we still have a 15/4 times sine phi d phi left in there. So that's going to give us a 2 pi minus 0. So 2 pi times 15/4, that's going to give us 15 pi over 2. And then we've got integral 0 to pi over 4 sine phi d phi. What is that? That's 15 pi over 2. And the antiderivative of that's going to be cosine, negative cosine phi 0 to pi over 4. So we're going to get 15 pi over 2 times, plug in pi over 4, and you're going to get negative root 2 over 2. Plug in 0, you're going to get 1. We're going to have, you're subtracting, and then the double negatives, you're going to get plus 1. And then you can simplify that. I guess I'll do it for you. All right. And so what that's going to be, so this is going to be 2 over 2. So we're going to get 2 minus root 2 over, and then 2 times 2 over 4 times 15 pi times 15 pi. Jeez. There you go. All right. And then I did one more example. Find the volume. We need to have a volume problem. Find the volume of the solid that lies within the sphere x squared plus y squared plus z squared equals 4 above the xy plane, and below the cone z equals square root of x squared plus y squared. All right, so the first thing you want to do is figure out what object are we talking about here. All right, so we've got the same cone that we had in the last problem. So we can go through and just kind of draw that in here. So all right, so it's below that cone now, not above it, but below it. So we want below that, above the XY plane. So it's got to be between the XY plane and the cone, and then within the sphere. So let's go ahead and just draw the sphere, and then we can kind of just try and figure out what it is. All right, so the sphere, drawing spheres. Actually not too bad at drawing spheres when I'm not using the writing tablet, but the writing tablet makes it hard. All right, that's not too bad. Okay, and so we could see if we look at it, so it's got to be above the plane, below the cone, within the sphere. So what's that going to be? Whoops, whoa. Things are going so well. So it's going to be, let's try a different color to kind of highlight it. It's going to be going to be this stuff. Right, so it's going to be it's basically going to be subtracting out this the ice cream cone top here. It's just going to be the stuff that's below that. It's where the between this curve here and this curve here, below it and below the cone. All right, let's see if we can set up the integral with that. All right, so first, whenever you're finding volume, what do? We do 1 dv over our object. And then once we've done that, we can go ahead and just pop some stuff in there. So dv, we know with spherical coordinates, that's rho squared sine phi d rho d phi d theta. And then what rho values would we have? So it needs to be inside the sphere. All right, so this sphere that we've got here, this is the sphere is rho equals, now it's the radius of the sphere. So the sphere that we've got here is radius 2, so it's rho equals 2. And then we want to go all the way to the center, right? So we want to, there is no inner sphere that we're subtracting out. So we want to go from 0, the very center, in the origin itself, all the way out to the sphere at 2. All right, and then in terms of thetas, I want to think about, where is the object defined? Is it defined above the x-axis? Yes, so that means we want to start at 0. And then if you go all the way around, is it defined above, all the way around? Yes, it is. So we want to go all the way to 2 pi. And then in terms of rotation, all right, so is the object, is part of the object straight up on the z-axis? No, it's not. The object does not start until we get to the cone. So we want to start at the cone at pi over 4. Okay, that's this angle here. And then we want to stop when the amount of rotation hits the xy plane. So we want to stop at the xy plane. The amount of rotation for the xy plane from the z-axis is going to be pi over 2. All right, and then so there's our integral. And then from there we'll see if we can fit this in. This doesn't look like very much space, but we'll try. All right, so it's going to be rho cubed over 3, 0 to 2, sine phi. These are a little shorter, I think. The volume problems are shorter because you have less stuff inside. Anyway, so you put in the 8/3, so we get 8/3 pi over 4 to pi over 2, 0 to 2 pi sine. Oops, what, I got the order wrong. Did you catch that? I used to do the order the other way. That's why. For some reason, I like d phi d theta better. All right. Anyway, hold on. Let's just do the antiderivative here. The antiderivative with respect to theta is just theta. So do theta 0 to 2 pi, and then sine phi d phi, and then we got 2 pi. Move that out, so you get 16 pi over 3, pi over 4, pi over 2. And maybe I just need to draw. Maybe I just need to write this smaller. If I wrote smaller, it would fit. And then what do we get here? So the antiderivatives, that's going to be negative cosine. So we have 16 pi over 3. We got negative cosine phi, pi over 4, pi over 2. All right, and then we've almost got it. So we're going to have 16 pi over 3. Plug in pi over 2. Cosine of pi over 2 is 0. And then minus double negative. So we're going to get plus. And then cosine of pi over 4 is root 2 over 2. And so multiplying that, what we're going to get 8 pi root 2 over 3, right? This and this cancel to 8. Yeah. All right, and so that is the last of the examples, and that is how you go through and do spherical triple integrals over spherical coordinates. Okay, thank you for watching. See you next time.